Lab 6, Magnetic Braking with Faraday. Here is our agenda. Introduction. We dropped a magnet down a non-ferrous aluminum tube. In real life, it took 1.27 seconds to fall down the tube, but in the simulation, it took 3.12 seconds for the magnet to fall down the tube. Main physics ideas and models. There's a general form for the magnitude of the magnetic field at a certain point of a dipole as expressed in this first equation, and then the EMF is the same as the negative change in flux over time, which is shown in the second equation. For our experiment procedure, we had a magnet with a calculated moment of 4.4 amps per meter squared. For the tube, the inner radius was 0.2 meters, the thickness was 0.8 centimeters, and the length is 46 centimeters. We dropped the magnet outside of the tube and inside of the tube. The system is the magnet, the roll of the aluminum foil, and the earth. The surroundings are everything else. It took 0.22 seconds for the magnet to fall outside of the tube, and then it took 1.27 seconds for the magnet to fall inside of the tube. For coding and simulation, this is what our simulation looked like. For coding the initial conditions, we set the variables as shown before. For the two equations, we just basically modeled what the equations were shown before, but this time in GlowScript. So this pink equation is the def dipole B with mu and r, and then the deflux over time is basically the same thing. For the calculation of the field, we basically had this equation that was also in the video, but in this case, sine of theta was mu hat cross b hat to get the sine, the magnitude of sine. And then basically we added up all the forces of the magnet for each of like the rings of the aluminum foil, and then we added that to F magnetic, and then the force net was the F magnetic plus force gravity, and then we updated the velocity and position of time. And then overall for the simulation, it took 3.12 seconds for the magnet to fall through the tube. So we said it took 3.12 seconds for the magnet to fall through the tube in the simulation, and it took 1.27 seconds for it to fall through the tube in real life. That means the simulation was off by 145%. Some possible errors are that the aluminum foil is not one perfect tube as simulated in the simulation. The magnetic moment calculations have their own errors discussed in the previous lab. And the magnet, when we dropped it, wasn't perfectly vertical. As shown in this video, it like wobbled back and forth. And then the mass measurement was an approximation of the magnet of the same type because we weren't actually provided scales to measure the mass of the magnet. Discussion. What if the resistivity of the conductor was reduced as close as possible to zero? How would the dynamics of the falling magnet change? In this case of a superconductor, the magnet would have almost an equal and opposite force opposing gravity by induction. The magnet would move extremely slow. And what if the holes or slots were cut into the tube? How would this affect the ring currents in your model? In this case, the currents would have like more turbulence, and the effect of the magnetic braking would be reduced, so the magnet would move quicker. The rings wouldn't look quite like rings, like the magnetic rings would like go around the holes cut in the tube, as shown. Thank you. This is one of the most fascinating demos and labs we've done with magnets, but I hope I never have to use GlowScript again.